All right, so number 44, we want to make this would apply enough force here so that this block right here doesn't slide, okay? Now just conceptually, how is that possible? If we are pushing on block 1, let's say, let's call this block 1, all right? And we'll call this block 2. If we're pushing on block 1, then what's block 1 doing to block 2? Pushing on it, okay? It's pushing it and force, and block 2 pushes backward. Yes, Katie?
It's like one of those like rides that spin really fast and then everyone takes the wall.
It is a very similar principle in that we will have a horizontal normal force. Everybody okay with that? That is the force that block 1 exerts on block 2. It's a normal force like this. Is it going to be smaller or larger than this force over here?
Smaller.
It is going to be smaller. You're right. So I'm just going to call this N for normal force. Now, do we have other normal forces in this picture? In this situation? Yeah, we do have normal force, what? Acting down on block 1? Up. Okay, so this floor, this surface here is acting upward on block 1 as well. But is that going to have anything to do with our answer? No, because this is frictionless, right? So if we're dealing with stuff that's going on in the x direction, the only reason we would care about stuff going on in the y direction is if we needed to concern ourselves with the normal force, which we would if there was friction present. Okay? So what we need to do is we need to apply a big enough force right here so that the acceleration of this system requires that this block exert on this block enough of a normal force so that the normal force times the coefficient of friction is equal to mg.
The normal force that you drew, the one that block 1 is exerting.
That is correct. This normal force right here is the force that block 1 is exerting on block 2. All right, so let's take a look at what's going on with block 2. Start with block 2 because that's really the situation that we're analyzing. All right, we already figured out we have a horizontal normal force being applied by block 1. We also have, obviously, mg, m1g if you want. In fact, let's just call this big M and little m, okay? That'll make it easy. We won't have to use subscripts, which can get cumbersome. No name jokes, please. All right.
Oh.
Just said no name jokes. All right, so what is it that's going to act upward to keep this block from slipping down? Friction. What kind of friction?
Static.
Yes. Static friction. So why did he draw a K? Nobody knows. All right, static friction. Okay? So now what we got to do is we know that if our situation works out correctly, net force in the y direction, we want to be 0. All right? The forces acting in the y direction are static friction acting upward and the weight, or mg, acting downward. And from here, I'll skip that set them equal to 0 thing. We could just say that we know that static friction has got to be equal to mg. Everybody okay with that so far? All right. So if static friction is equal to mg, how do we find static friction? Static friction is equal to, just like any friction, the fun equation. Mu times normal force is going to be equal to mg. Got that? So what we really need to solve for is which force? Normal force. All right. So normal force has got to be equal to mg over mu. That's how much normal force we need. Everybody okay with that? All right. And so what's our acceleration going to be? If that's our what other forces are acting to accelerate this block right here? This block right here. In the x direction, the net force is just what? It's just the normal force, right? All right, so I'm going to go over here and do what's going on in the x direction. The net force in the x direction is equal to, aha, this is what's going on. We do have an acceleration, right? Because we've got to figure out what acceleration of this block is going to give us a normal force that's big enough to hold that block up. Normal force in the x direction, what? This is still just the little block. Yes, block 2. That's what we called it, block 2. All right, so Fx is equal to, what is that? Looking at our free body diagram, it's just the normal force right here, right? All right, so the normal force. So from here we get mass of the little block, we're just dealing with the little block right now, times the acceleration in the x direction is going to be equal to the normal force. Aha. Now what do we have? Two expressions for what? Whoop. Two expressions for what? For normal force, right. All right, so we're going to take this one, and we're going to put those together, and we're going to say that MAX, the mass of the little block times the acceleration that we need, is going to be equal to mg over mu. All right, what do we see happening there? M's cancel, okay? So we know that the x acceleration has got to be equal to g over mu. The acceleration has to be that big in order for what? In order for the normal force to be big enough so that the block doesn't slide. Okay? Everybody got all that? Yeah. So far all we've done is figure out what the acceleration of the little block has to be. But if the little block and the big block are a system, then that also has to be the acceleration of what? The system. The entire system. Very good. Okay, so now we know, I'm going to go to a new page for this. We know that AX is equal to G over mu. All right, I'm going to copy that. We'll go to a new page, paste it in. All right, so this is true. So now we're going to deal with, I'm going to just do a sketch here real quick. All right, we've got these two blocks now, and now we have the entire system. So we know that the acceleration of the entire system has to be this as well. All right? So now we need to know, remember that this force right here, the one that was coming in this way, isn't that the net force acting on the system?
Yep.
It is. Okay, if we're to draw a free body diagram for the system, this is that big net force, that big blue arrow we drew in the other one. And again, we have normal force. This is going to be a vertical normal force acting on block 1. And then we have acting downward on the system, the whole system is, whoops, mmg, right. M plus M times G. Okay? Now there's some complications going on here. It's actually, what we really need to worry about though is the x direction. Okay? So we'll skip what's going on in the y direction. We don't have to worry about friction along that surface. All right, so now net force acting on the system in the x direction is equal to what mass though? The whole mass, m plus little m times that ax we just found. And we know the net force acting on the system is just that applied force F that we were talking about. So now we come down here, we're looking for the applied force. Applied force is equal to the sum of the masses times AX, or what did we decide that A is? Mu over, or G over mu, right? All right, so the force has got to be equal to M plus M times G over mu. So is that going to be bigger than G or smaller than G? Bigger, because mu is less than 1 in this case. It's given to us. All right, so force is equal to, what's the big block's mass? 25 kilograms plus little mass? 4 kilograms times G, 9.8 meters per second squared. Mu they gave us as 0.71. That's pretty frictiony. All right, so what are the units for mu?
None.
There are none. Right, it's dimensionless. So we have dimensionally, we got kilogram meters per second squared. What is that, everybody? Newtons. All right, we're looking for a force, so we're in good shape dimensionally. All right, so 29 times whatever it's going to be. What's it going to be, Philip?
I believe it's 40.845.
40.845. We'll stick to 40.8 newtons. Okay? 40.8 newtons is the answer that we got. So let's go check that, and then we'll come back.
I messed up.
Okay, we have an alert here. Is that this is off by an order of magnitude. If we were to look at this, we got to say, all right, this is 29. This is going to be bigger than 9.8, probably bigger than 10, right? Considerably bigger than 10. All right, so we know that we got to have something in the hundreds. So order of magnitude check there gives us that we were off some. So the actual answer is, it's like 400.2 or something like that, but we'll say 400 newtons, or if you prefer, 4 times 10 to the second newtons. All right, that's why we check our work. Thank you.